in Blackboard, just like I have on all the others. And so I'm going to pull this out of the way, and I'm going to present to your monitors, I hope, here in just a second. Let me get this guy working. Okay, so I think the first thing you're going to be seeing is Blackboard. And just as a reminder, of course, in Chapter 5, when you click on that and you log in, I'm going to have to log in, and click on our section, and then you go to Chapter 5. There are, to start, there are a bunch of videos, and the first 3 videos cover dimensioning basics, and those are important to watch, and those cover the things that you've been doing the past since the last period when we were looking at putting dimensions on. But the next 3 here talk about tolerancing, and these videos are actually sort of the crux of dimensioning. It's like, what does a designer go through when they tolerance a part and they come up with all those dimensions that you guys use when you're a drafter to draw those views? So the process for a designer is looking at all of the features on a part and then thinking about what's the largest that feature could be and this part still work, and what's the smallest that feature could be and this part still perform its function. So it really gets down to that, and that's what these 3 videos cover right here. And of course, then when you scroll down, you have your assignment folders, and each of these assignment folders has in it a video showing you how to set up your dimension style for that project, and then a video showing you how to place the dimensions for that project on the views. And so these are all good videos in here to watch as well as you complete this work over the weekend, because the goal would be to have all 4 of these done by the next time we meet on Monday at 11 o'clock. The reason for that is that on Monday what we'll be doing is opening up the guest cottage and putting dimensions on it. So on Monday we'll talk about architectural dimensioning and how you create an architectural dimension style. And we only spend 1 day on that project. It goes pretty fast. So, but these 4 projects here are really important because it's 4 grades for your daily work. So let's talk a little bit about tolerancing today. And so I always think of tolerancing as this is what you have to know in order to be a designer. So I'm going to hopefully project to your monitor now. I'm going to back up a little bit in this. Okay. All right. So hopefully you're seeing what I'm seeing now. And what I wanted to show you guys is a scale called the 10 scale. And we've looked at this before. This is called the engineer's 10 scale. This is a common scale in a mechanical engineer's office when they're designing machine parts and measuring things. And so what it gives you is inches broken into tenths of an inch. So if you go to 1 inch and you go 5 more of these marks, you're at 1.5 inches, 1 5/10 of an inch. So I'm going to go to the next slide. So let's just look at a dimension that's broken down into 3 places of precision. The first number that we see there represents whole inches. So this would be 3 inches, and then we have our decimal point. And to the right of the decimal point, we have the first digit is tenths of an inch, and the second digit would be hundredths of an inch. The third would be thousandths of an inch. And it's pretty rare to see anything beyond that because of the expense it would cost to be, building parts that are a 10,000th of an inch of precision. That's really starting to get out there, and it would raise the cost of your parts. In fact, even a 1,000th of an inch is going to raise the cost of your parts a bit. So here we have 1 place precision, 1.5. Here we have 2 place precision, which takes us to hundredths of an inch, where this one over here took us to tenths of an inch. So you can see each of these is a tenth, so 1.5 would be right there. 2.75, we would go to the 7, 2.7, and then we would go halfway to represent the 5 hundredths of an inch. And then 3.125 would be 3 1/10, and then 2 more hundredths, and then 5 thousandths of an inch. And that would put us out here somewhere about, that represents 1/8 of an inch, actually right there. But for most of us, that hundredths and thousandths doesn't mean a whole lot. To give you an example of thousandths of an inch, if you took a sheet of printer paper, like common 20-pound printer paper, and you put it on a surface, and you put your finger on it, and then run your finger off the edge of it so you can feel the drop off of a sheet of printer paper from the top of the paper down to your desktop, for example, that is about 4 thousandths of an inch right there. Okay, 0.004. And so, for most of us, that's about as thin as anything we deal with would be maybe a sheet of paper. So that gives you some idea of what a thousandth of an inch is like, or 4 thousandths of an inch. So anyway, the way we would refer to this 1.5 is we would say 1 5/10 inches. This 2.75 we would refer to as 2 75 hundredths inches. And then this guy over here would be 3 125 thousandths inches. Now, this is how machinists talk in a machine shop, and how, they refer to everything pretty much in thousandths of an inch. At least in North America, they would probably, if they were set up in the metric system, it might be different. But in North America, the common precision for like a CNC mill or a lathe or something like that would be in the thousandth of an inch setting. And so machinists kind of think in thousandths, and they actually call a thousandth a thou. Okay, so we'll get into that a little bit more. So here's a scale broken into 4 inches, where each of the marks represents 1/10 of an inch. Okay. Now, if you took a 1/10 of an inch and you divided it into 10 parts, you would have 100th of an inch. So right here we're seeing 1/10 of an inch, and right here we're seeing 5/10 of an inch. But when we go to the next slide, we're taking one of those tenths and breaking it into 10 more inches, and what these would represent is 100th of an inch. And so instead of saying that this is 0.1, if we're looking at hundredths, we think of it as 10 100ths of an inch. But it's actually the same as having a 1/10 of an inch, but we're breaking it down into 10 equal parts. So that represents hundredths of an inch. So this dimension over here we might read as 52 100ths of an inch, and we would write it as 0.52. All right. So this is 2-place precision. Now, if we took 1/10 of an inch and we broke it into 10 parts, so each of these marks up here represents 100th of an inch. So we start at 1/10, we break one of those tenths into 10 parts, we're at 100th of an inch, 0.01. But then, if we take one of those hundredths, so here's 100th of an inch, and we break it into 10 equal parts, each of those parts would represent 1,000th of an inch, 0.001. Okay, so we go from 100th of an inch here, from 1/10 down to 100th when we break it into 10 pieces. Then we go down to 1,000th of an inch, and 1,000th of an inch is 0.001, and the fundamental unit of measurement for many machinists is 1,000th of an inch. And so, as I said, for this reason, machinists often refer to 1,000th of an inch as 1 thou. So if you're ever in a machine shop, rather than saying 100th of an inch, a machinist will probably imagine that has that 0 on there. And so you're in there talking about 100th of an inch, and the machinist says 10 thou, and it means the same thing, because 0.1 is 100th, but 0.10 is 10 thousandths, which is the equivalent of 100th of an inch. Machinists don't usually use hundredths. They, like I said, they're going to say 10 thou. So the dimension above, right here, this 1 or 0.001 would represent 3-place precision. And as I said, the thickness of a sheet of common 20-pound printer paper is about 0.004 thousandths of an inch. All right. So you can even break a thousandth of an inch into 10 parts and get down into 10 thousandths, which machinists refer to as a tenth. And not to be confused with 1/10 of an inch. When a machinist says a tenth, they probably mean a 10,000th of an inch. But as I said, that's pretty rare when you get down into that. But I wanted to point out a couple of things in this slide right here. Things I've already said, but then I've got a couple of different things I want to point out to you. Right here, the diameter of a quarter is 0.955 inches. So we would say that that's 955 thou, which is 45 thousandths smaller than a full 1 inch in diameter. So a diameter of a quarter is a little bit smaller, 45 thousandths of an inch smaller than a full inch. Okay, just to give you an idea. So there we see it, the diameter 0.955, 955 thou. So 0.001, which is 1/10,000th of an inch, or 1/10 in machinist speak, not to be confused with 1/10 inch. And so back to tolerancing. So back to tolerancing, what a tolerance is the less perfect a feature can be and still perform its function, the less it costs to manufacture. So what tolerance is, you know, a designer looks at a part and says, how perfect does this part have to be? If it can be less perfect, it will cost less to manufacture because the manufacturer can probably manufacture it faster and with less setup time and that sort of thing. So the more tightly you tolerance parts, generally the more they're going to cost to manufacture. Okay. So designers are always looking for what's the loosest tolerance that you can give to the manufacturer and the part still perform the way that it has to perform. Okay, so it can't be too loose where things rattle around or things move around. So it's trying to find that exact tolerance that you can use. So a definition of a tolerance is the total permissible variation in a dimension value, the difference between the upper and lower size limit of a feature. And so I'll show you some of that in just a second. But so a feature is a geometric element that is added to a base part, such as a slot, a surface, or a hole. So that's what a feature is. Tolerances are applied to the upper and lower size limits of features. So here's an example of a part where we have a dimension saying that from this edge here to the top edge is 1.00 inches, and then here comes the tolerance, plus or minus 0.01. Now that is 1/100th of an inch, right? If you added another zero to it, like a machinist probably would, they would say that that's 10,000th of an inch, but 1/100th is the same. So what that means is when you manufacture this part, afterward you would inspect it and you would measure from this surface to this surface up here. And as long as that distance between here and here fell between 1.01 and 0.99, then this feature would pass inspection. Now there would probably also be a dimension from this side to this side that would also be tolerant. So you would just keep inspecting this part feature by feature to make sure it was within tolerance. Okay, so now we get back to the ASME Y14.5-2009 dimensioning standard. What the standard says is this: each dimension shall have a tolerance. So that kind of locks us into thinking about, for every dimension that we have, we need to have a tolerance. Now there are a few exceptions, and I haven't explained those yet, but let's just think in terms of that every dimension shall have a tolerance if you're dimensioning per the ASME Y14.5 standard. So I'm going to skip through some of this. Here we go. So here we have that plus or minus tolerance again on 1 inch. And over here we have the same thing applied in the metric system. And so what this is 1/10 of a millimeter over here, because these are in millimeters, and this is the imperial system over here. These are in inches. Okay. So the size that we specify that you can add or subtract your tolerance to, we refer to as the nominal size. So here's the nominal size, and here is the tolerance. Here's the nominal size in millimeters, and here is the tolerance over here. Okay, so the nominal size is used to describe the general size of the features. Tolerances are applied to this dimension. Another way you could list your dimensions with tolerances is you could use what are called limits tolerances, where instead of saying 1.00 plus or minus 0.01, you just list the widest or the tallest this part could be and the shortest this part could be instead on your dimensions. That would be another way to do it. And you could do the same thing with millimeters over here on the right-hand side if you wanted to. So there's your upper limit of size. That would be when it's at its tallest. And here's your lower limit of size when it would be at its smallest size. So I want to show you a part now. And I'm going to turn on my highlighter. Probably should have had it on already. Change the color. And I want you to look at this slot right here. Okay, you see that slot? So how wide is that slot going to be? So just study that for a second. And what you'd see is that if you measure from this datum feature, this guy over here is called the datum feature, and you measure over 1 inch, you would have this feature right here, which is the edge of that slot. That would be 1 inch. And then if you measure from the datum feature here over to this side, and you subtract those two, your slot would be 1.00 inches. But that's if you don't apply any tolerances to it. And we've already seen that the ASME standard says each of these dimensions right here has to have a tolerance. So here's a different way to tolerance or to dimension that same guy, where you have from here to this edge is 1, but then instead of coming back to your datum feature like you did on the top, oh, my mouse has disappeared, there it is. See how we came back to the datum feature up here? We just picked up where this edge ended and we just added the slot at 1 inch. So the slot width here is 1 inch and the slot width up here is 1 inch. That's because there's no tolerances involved. Both of those would be the same. This one up here we call baseline dimensioning. This being our baseline over here on the left-hand side, that datum feature. So a baseline looks like kind of a set of stairs. They're getting taller or longer as they go up. Where continuous dimensions, you put one dimension in, and then from where that dimension ends, you add another. So this is continuous, and this is baseline up here. When no tolerances are involved, the width of that slot is exactly the same. It's going to be 1.00. Okay, but when we start to add tolerances to it, things start to get a little bit different. So let's look at our same part dimension using baseline dimensions, but with tolerances. Okay, so let's say that our manufacturer makes this distance from here to here at 1.00 minus 0.01. That would make that distance right there 0.99. Right, from here to here, and that would pass inspection. Then let's say that the next cut they make on this guy right here, they go to 2.01 instead of exactly 2. So they make this 2.01. Now how wide is the slot going to be? Well, if we take 2.01 and we subtract 0.99, we're going to come up with 1.02. So we see the difference in what tolerances how they affect our parts. So tolerances are something that are really important, and they play a big part in, how tight fitting or how loose fitting things are going to be. Because if you were designing another piece that had to fit inside this slot right here, you would want to know what's the narrowest that this slot could ever be and what's the widest this slot could ever be. That would be something you would have to know, and you would have to use your tolerances to calculate that. So this calculation that we're seeing over here, this is what makes you a designer when you start doing calculations for your parts. And designers make more money than drafters, because designers are going to write on this on a sketch what the diameter, or what that distance should be, and then the drafter gets it and just draws it that size, like you guys have been doing. You didn't design the bracket, but you are being the drafter. When you draw the bracket and you put dimensions on it, you're working as a drafter or CAD technician. If you had designed the bracket, you would have been paid more, because that's more responsibility and you're thinking more about it. And so our goal at ACC, when you come into our program, if you stay in our program, is we want you to graduate and understand how designers work so that you can go out and get a job. Your first job would probably be, they'll start you as a drafter, but once they realize you can design, hopefully you're going to start to advance within their system and start making more money. Now, let's look at a continuous part. This part has been dimensioned continuously, and so let's do the same thing. Let's say that they go 0.99 again from here to here, just like they did on the one above. So that's within tolerance. It's 1.00 minus 0.01. That would be 0.99. So it would be 99 hundredths of an inch. Well, what's the widest this could ever be up here? Well, this dimension is independent of what's going on over here. The widest this slot can ever be is 1.01, and the narrowest it can ever be is 0.99. But up here, because we dimensioned using baseline, we could wind up with a slot that's 1.02 wide, because of the effects of these two dimensions, this dimension and this dimension here, because they kind of affect each other. Where down here, the width of our slot is controlled just by this one number and its tolerances. So the point is that, I'm going to back up to this guy right here. If you don't have tolerances, you can dimension using continuous or baseline, and the width of your slot would be the same. So with no tolerances, they're the same. So what happens is drafters start to think, it doesn't matter how I dimension these parts. I can use baseline or I can use continuous and I'll get the same. But what we learn in this is that if you use baseline, it will give you different widths of that slot than if you use continuous. Neither one is better than the other. It just, it depends on what the designer wants. Okay. So the moral of the story is this: if the designer gives you a sketch and they use baseline dimensions, when you dimension, you should use baseline dimensions. If the designer gives you continuous dimensions, you should use continuous dimensions when you draw the parts and put dimensions on them. To do otherwise, you could change the design intent of the designer. Okay, so we can see right here that the baseline dimensions could result in a slot measuring between 0.98 and 1.02, where down here the slot width, the narrowest would be 0.99 and the widest would be 1.01. And as I said, it's not that one of those is better than the other. If the designer is okay with a looser tolerance like you get up here, then they might dimension it baseline. If they want the tighter tolerance, they might go with the continuous dimension. Now, as I said earlier, the tighter the tolerance, though, it's possible the part is going to cost more to manufacture. So that's something to consider in the design of parts. So you have kind of the designer's always asking themselves is, what's the most tolerance I could give and this part still perform the way we want it to perform. All right, so if you're doing some kind of rough part that's going to go on an oil rig somewhere, you would probably give really loose tolerances, especially if you want things to assemble quickly or come apart quickly. You want to give loose tolerances. If you're designing an Omega watch that an astronaut's going to wear when they go to the moon, you might tolerance that thing pretty tightly to make sure that the effects of weightlessness or anything like that don't affect the mechanism of that watch. Okay, and that's exactly what happened when the astronauts of Apollo went to the moon. They tested a bunch of mechanical watches, and the Omega like Dive Master or something, Speedmaster they found was the best one, and so all the astronauts wore those Omega Speedmasters when they went on those trips to the moon. Of course, now those watches that the astronauts wore are worth a fortune. So anyway, so the way we display tolerances on a technical drawing, a lot of times is though we will put them in our title block like this. And so what this means is that any dimension that's at 1 decimal place, so let's say we've got a dimension that's 1.5. What that would mean is that the tolerance that would apply to that is plus or minus 0.05, 5/100ths of an inch. So that's a pretty generous tolerance right there. If we had the same dimension and it went to 2 decimal places, our tolerance changes. It goes, now it's at plus or minus 0.02, 2/100ths of an inch. If you go to 3 places, so you have 1.500, your tolerance, according to our title block over here, is 0.01, so 1/100th of an inch. Now, as I said, the machinist is going to put another 0 on there and call that 10,000th. And if they look at this tolerance, they're going to put another 0 and they're going to call that 20 thou. And they're going to add another 0 to this, and instead of calling that 5/100ths, they're going to call it 50 thou. And they mean the same thing. And so I always point that out to students because, when you get into a machine shop and all of a sudden the machinist is using a different language than you have, it's a little confusing sometimes. So I wrote right here that incorrectly labeling the precision of a dimension may change design intent, and an error that changes design intent can lead to serious consequences. And the worst situation could be that because you screw up the design intent, what if you make thousands of parts that don't actually fit or function as designed, and those parts have to be remade? Or, like in the case of the auto industry, they have to do a product recall. You can imagine what that costs a company to do a product recall or to have to remake a bunch of parts. So this is why drafters need to be really careful when they're dimensioning and make sure that your drawing reflects exactly what the designer's input showed. Okay, so we want to dimension from the same datum features that the designer showed, and we want to use the same precision as what the designer showed us on their sketch. So, in our case, generally everything we're going to get, I'm going to kind of flip through some of these guys right here to get to this one. Everything that you're going to be given is going to be a sketch in this class. So you're pretty much going to be looking at the designer's sketches right there. And so you want to just make sure that if they're at 2 places, that you put it at 2 places. If they're at 3, you put it at 3, because it will affect the tolerance. Now, I want you to look up here, though, at this drawing. And right here we have a dimension with a tolerance of 1.00 plus or minus 0.01, and then we have another tolerance dimension right here, and a third here. So what's the widest that this part could ever be? Well, if this was 1.01, so we got 1.01, and then we have 1.01, and we have 1.01, then our part could come out to be 3.03 if we add all of those together. So the designer looks at that and decides, is that okay or is that not okay? So here's what the designer couldn't do, is come in here and just say 3.00, because what that would mean, since everything has to have a tolerance, is that that would also be a 3.00 plus or minus 0.01. So that would mean that if you tried to dimension this way, the widest the part could be would be 3.01, right? But down here, you're allowing it to go 1.01, 1.01, 1.01. So the point is, it can't be both ways. You can't have 3.00 up here and then 1 and 1 and 1 plus or minus 0.01 down here. So what you do in a case like this is you take the 3.00 that you have up here and you put it in parentheses. And by putting it in parentheses, it says this is just a reference dimension. And what that means to the manufacturer is, don't make the part using this dimension here, and don't inspect it using this dimension here. This is purely for reference. So that's what putting something in parentheses means. It means it's a reference dimension. So when they make this part, they're going to use this dimension and its tolerance, and they're going to use this dimension and this dimension and their tolerances. And so the part might wind up being 2.03 wide. It could be as narrow as 2.97. So of course you wouldn't have parentheses around that, but the parentheses happen right around this guy right up here. It has to be a reference dimension. All right. So I think probably have a bunch of that written down, but I'm going to skip through some of this. Now, one of the notes that I have that kind of wrote over the top of, just want to point something out to you. This phenomenon where we have 1.01 plus 1.01 plus 1.01 and our part keeps getting larger or smaller is called a tolerance accumulation. All right. And you have to be aware of things like tolerance accumulation, because it can mess up your design intent. So designers are always thinking about things like this. What's the worst case if I make all of these 1.01, 1.01, so that this part winds up being 3.03? Well, if I were designing this part, I would wonder, does this part from this datum feature here to this datum feature over here, does that have to fit precisely between two planes or something? And if it does have to fit between those planes, if it's 3.03 or if it's 2.97, how is that going to affect my part and how it works in that assembly? Okay. So I'm going to skip through this part and talk a little bit about the cost. So we said that designers consider the cost when determining the tolerance for a feature, because as tolerances become tighter, the cost goes up. And one of the reasons for that is it may take longer to manufacture the part. It may be because of tighter tolerance, fewer parts will pass a quality control inspection. So there's a lot of things that can affect it. And the designer, as I say here, walks a fine line between the desired accuracy of the part and the cost of manufacturing the part within the budget. All right, so a minute ago I referred to an Omega watch that an astronaut might wear. Well, if you walked into a store to buy that watch, it might cost $5,000. And if you walked into Walmart and bought a Timex, it might cost you $49, right? Well, part of the thing you hope you're paying for is better manufacturing on the Omega and closer tolerancing and all that kind of stuff. So, I don't know that actually is built into those parts that much where it should cost $5,000. But the point is that you would hope that the tolerancing was a lot stricter on the Omega watch than on the Timex watch, based on what the differential in cost is. But you think about if you're going to design a Lexus, right, and you're going to sell that Lexus for $80,000. You have a little more leeway to tolerance your parts in that Lexus tighter and closer. So when you close the door on the Lexus, it sounds a little bit different because all the parts fit so snugly and stuff like that, right? But if you had a really cheap car that cost $12,000 on the car lot, like maybe there's some Hyundai or something like that, or some Chevy, some Volt, or not a Volt, actually a Bolt, I think is what they got anyway. You can see the difference between an $80,000 Lexus and a $12,000 car. A lot of that could be built into how much more money you have to spend on tolerancing the parts in that Lexus. Okay. So anyway, that's just something to think about. Now, we offer a course here at ACC, and you can actually take it next semester. And I usually teach this course, but I'm not teaching it next semester, but it's DFTG 1433. And it's called Mechanical Drafting. And in this course, we don't use AutoCAD, we use a software called Inventor, and every machine part that we make, we create a 3D model of it. And when we dimension things, we talk a lot more about tolerancing in DFTG 1433. And we also talk about other considerations of tolerance, things like form, where, we haven't even talked today about, when you have a surface, is that surface, how flat is that surface? If you're talking a few thousandths of an inch, you could have a surface that's kind of wavy. How straight is an edge? How circular is a cylinder, or from the end view? And then over the length of that cylinder, how cylindrical is it, which we call cylindricity. We can also say, let's say you have two planes that meet each other right here. How perpendicular do they have to be? And if you have angles, how precise does the angle have to be? So these are other ways of controlling your parts, not just size, but also the form. So how parallel, how perpendicular, how flat, those sorts of things. So, and that's called geometric dimensioning and tolerancing, or GD&T. That's one of the things we cover in DFTG 1433. And you can take it next semester. It follows this class. So all you have to have as a prerequisite is DFTG 1405 if you want to take that. So we're offering 3 sections of that in the spring. Well, this is actually in your book, and I put it into a video, and so I'm not going to go through all this, but it takes you through how do you tolerance a cylinder, and then how do you tolerance a hole that cylinder might fit into. All right. And so what you do, you have to focus in on what's the smallest diameter the hole can be, what's the largest diameter the hole can be. Let me back up one. Then what's the largest diameter the cylinder can be, and what's the smallest it can be. So you can see it's smaller. It's starting at 0.98, and when you add plus or minus 0.01, the greatest diameter that cylinder could ever be is 0.99. And when we go over here and we look at this hole, if you have 1.00 and you subtract 0.01, which would make it the smallest, it would be 0.99. So the question is, would the cylinder at 0.99 still fit into the hole at 0.99? And what we would do is we would subtract the size of this from the size of this, and if it were 0, which it would be, we would say there would be no interference. Now, you would have to line up that cylinder exactly perpendicular to the hole shaft to make sure that it goes through. It would be hard to fit the 0.99 cylinder through the 0.99 hole, but it would be possible because there shouldn't be an interference. So what the designer could do is that instead of going with 1.00, they could make the nominal size of that 1.01 plus or minus 0.01. And that way the smallest the hole could ever be would be 1.00. And since we know the largest this could ever be is 0.99, we would be assured of a clearance of 0.01 inches in that case. All right, so this is how designers manipulate the size of features to make sure that things fit the way that they want them to fit. So as I said, when you go into Blackboard, there are three. I'm going to click on, get out of this guy for a second, sorry. When you go into Blackboard Chapter 5, there's 3 videos on tolerancing. And the last video says apply what you've learned, and that kind of takes you through some of these simple design problems and calculating the tolerance on those. And so these 3 videos right here cover what I covered today, except more in depth. So the first 3 just cover the basics of dimensioning. The final 3 cover actually how you tolerance things. And I don't know if I told you guys the other day, I think I told my other class, that I have these 2 videos out there on the internet. One's called Maximum Material Condition and Least Material Condition, and one is called Calculating Fit Between a Cylinder and a Hole. And those videos are the most watched videos on my site, and like I have over 100,000 views on some of these from people all over the world who are trying to figure out how to calculate tolerances on 2 parts. Okay, because it comes up all the time in an office, and it's something they don't teach you when you go to engineering school. So these guys are very popular, and so these are other things that are out there at that YouTube site that you can watch if you want to, but a lot of it's covered in these 3 here. Okay, so last thing I'm going to do is click back here on AutoCAD, drag this over. So hopefully you guys are seeing AutoCAD. Is that correct? Are y'all still seeing AutoCAD? Looks like you are. I'm sorry, I'm having a little bit of trouble with getting my, here we go. So let me check the chat. Yeah, okay, good. Thanks, Haley and Grant, for saying that. So I have these 2 parts here, and you guys have already seen how to make a dimension style. So if you pick on this button right down here, it takes you into dimension style. So what I did though, I made a dimension style that I called toleranced. And it had the same dimension setting as these ASME small radii dimension style. But I made one change to it. I'm going to click on that. I went over here to tolerances, and I changed my method from none to limits. And then I put in a tolerance of 0.01. Okay, so that's 1/100th of an inch for my upper and lower value, and picked OK. And then I'm going to pick on that and set it current. And just to give you an idea, so if I put a diameter dimension on this hole right here, it tells me what the greatest diameter that could be, 1.01, or the smallest diameter that could be. Right, so by putting on the tolerance dimensions, these are actually the limits of size. I can dimension things, and it's more apparent to me what the size of everything is. And so if you're trying to locate the centers of that hole, and you look at that right there, it makes a little bit different to think that the center of this hole, when measured from this bottom edge right down here, could be as high as 1.01 or as near to the bottom edge as 0.99. Same way with this. If this is my datum feature on the left-hand side, that the center of the hole along this axis, the x-axis, could be 1.01 or 0.99. You can see that the center of this hole can move quite a bit and still pass inspection. It can move to the right or the left by 0.02 of an inch. And it can move up or down by 0.02 of an inch. And then on top of that, the diameter of the hole could be as great as 1.01 or as small as 0.99. So even on a simple part, when you start to add tolerances to it, things get complicated. And so when you're a drafter, you just come in here and you put those dimensions on, and you don't give much thought to what the tolerances are. But if you want to make more money and become a designer, then you definitely will get more focused in on how to tolerance your parts. So the new assignments are the tool holder, which I'm going to click on back down in here and go back to model space. So you're going to be placing your dimensions on here. And I want to point out right here that when you do your check print, you're going to see that this says 7.00 and it's in parentheses. Now when you put that dimension on and you just go from here to this corner and you bring it up here, oh, that's weird, I'm getting this 7.01 for some reason. What you're going to see is 7.00. To put those parentheses on there, you're going to double click on it and you're going to have to actually type in a parentheses at the front and the back of it. And sometimes you'll lose the whole thing. So you do your 7.00 like that. And as I said a minute ago, this is called a reference dimension, which means don't make the part with this and don't inspect it with that. So let's see why that's a reference dimension. If you look at this dimension right here, from this edge to this point right there, it's 4 inches. Okay, so that will have a tolerance on it, a plus or minus whatever the tolerance is. From that edge right there, if we look at our top view, we have this dimension right here, 2.25 plus or minus its tolerance. All right, so the location of this hole can be moving based on what the tolerances are. And then on top of that, we have a toleranced radius of 0.75. So the distance from here to there may be exactly 0.75, or it may be 0.75 plus or minus 0.02, or whatever the tolerance on this part is. Remember, to find the tolerance, we click on this and we go look at our title block. So anything that's at 2 decimal places is plus or minus 0.02. So you can see that the actual length of this part, which from here to there is 4 plus or minus its tolerance, and then from here to here 2.25 plus or minus that tolerance, and then from this center to there 0.75 plus or minus that tolerance, that the actual length of our part could be more than 7.00, or it could be a lot less by 0.06 of an inch from 7.00. So we have to make one of these dimensions a reference dimension, and so we're going to make the 7.00 a reference. So that would mean that the designers looked at this and said the overall length of this part is probably not that important. It may not fit into anything. So that's just one of your considerations on this. The other thing is that, like on the shaft guide, when you dimension the shaft guide, we pointed out to you that this cylinder that you have right there should be dimensioned in the side view. And that's an ASME Y14.5 rule. You dimension cylinders in their side view. Now holes you can point to. So we've got a diameter of 19. This is a hole right there. But this is the end view of that cylinder. So we need to dimension that over here. Well, the same thing happens on our tool holder, is that we have a cylinder right here, and you can see it in the top view, and that's the edges of it right there, and it sticks up 0.25. So there's a cylinder sitting on top of the surface, and we have to dimension cylinders in their side view, and we have to put a diameter in front of them. So that's why we're going to have diameter 1.25. Now I'm going to go ahead and just throw another dimension on here. When you put that dimension on, well, that's weird. I don't know why I'm getting these weird numbers. What that is, even though this is a cylinder, AutoCAD just sees that as 2 lines. And because it's seeing that as 2 lines, it doesn't know that's a cylinder. And so what you have to do is come in here and double click on this, and you need to put the diameter symbol in front of it. And the way you find your diameter symbol, you double click on it, you go right up here to your ribbon where it says symbol, pick on the down arrow, and you have a degree symbol, you have a plus or minus, and you have a diameter symbol. And one of the things that shows you there is %C. AutoCAD years ago, when it started to have symbols like diameter stuff, it didn't have them on a keyboard and it didn't have the ribbon yet. So it tried to give you a way where you could get AutoCAD to write a diameter. And so if you typed %C and pressed enter in front of this dimension right here, it would put a diameter symbol, and it still does that. Or you can just pick diameter and it'll put a diameter symbol in front of yours like that. Okay, so that's what you're going to do. Of course, yours is not going to say 1.24. I don't know what's going on with this part, why everything looks like it's off just a little bit, but anyway. So that is your third project, and you can see there aren't that many dimensions you have to put on here, but you know. And then your fourth project is this guy right here. Let's zoom in on him. Okay, so we have our front view, side view, and top view, and I want to caution you about something. If you look on the sketch for this one, on page 299, and you look at the width of this piece right here, on page 299, it says the width of that is 2.250. So the designer is intentionally tolerancing that to 3-place precision. So you need to make sure that you put that at 3-place precision right there, or I would count off as a -5. That would be changing design intent. Now, why would the designer go to 3-place precision? If we go back over here, we look at that. 3-place precision is plus or minus 0.01 inches. So 1/100th or 10,000th of an inch. What we have to imagine is that this, from this side to this side right here, that fits in somewhere, or something fits over it, or something's happening where the designer wants to tolerance this tighter than most of the other dimensions, which are at 2 decimal places. So pay attention to that when you put your dimensions on here, to make sure that everything that's 3 places is 3 places, and anything that's 2 places is 2. Okay. All right. So I don't see much else that we need to deal with. These are fairly straightforward in putting the dimensions on, I think. On this one, remember that putting an angular dimension, that you have a tool for angular dimensions. It's right here, angular, or you can find your dimensions. You pick up here, you got aligned angular, and then radius and diameter and so on like that. Okay. All right. So I think that's everything that I have. So these 4 assignments are due on Monday. Now, when I say they're due, I'm not actually going to count off for them on Monday. I'm going to put a due date in of, I believe it'll be the following Wednesday would be the due date, where there might be a late penalty, because it may take you a little while to turn these around after you print them and get them to me, and then I'll send you the check print, and you know you're going to be doing other stuff. So, but you'll make your changes and then send them back. So when I say the due date, what I'm talking about really is the final drawing sent back to me with all the dimensions on it after it's been checked. Okay. All right. So, any questions? And if there aren't, I'm going to stop presenting here, and I'm going to end my video.